That was a clap sync. Here's another one. So, for some of you, this is going to be pretty weird because I'm not really a math guy. Not a lot of you know me as a math guy, but I am a math major. I am in university studying mathematics, and I'm going to get my master's degree in mathematics eventually, sometime, probably, hopefully, in 2 semesters. So in December 24, that's the hope. Since I'm donkey dog buns at Anawysis, I thought I would do something. I'm going to take this book, Real Analysis, a long-form mathematics textbook by J. Cummings. It's got like 9 chapters on analysis stuff, and it's got a bunch of good exercises. And so what I'm going to make is a series called Weal Anawysis Wednesday. That's a Real Analysis Wednesday with a bunch of W's where they shouldn't be, because I got to make it fit with Wednesday. And I'm going to try to get through the whole thing, front to back, start to finish, no matter how long it takes or how much I have to break it up, because I want to be good at analysis, and I'm not. And even though I got A's in my analysis classes or whatever, don't let that fool you. I feel like I could be a lot better. I feel like I'm slow and not that creative in analysis. And so I'm doing something to change that. And I'm uploading these videos for anyone that wants to watch them, I guess. I went to this guy's website, longformmath.com, and I thought I was going to be really upset because he was going to have all of the solutions just there, and it would be not as special that I'm going through and solving all of these exercises by myself. But I went there, and he's only got like a maximum of 10 for each chapter just readily available, which is going to be nice. I wonder really if I would be maybe the first person to upload a solution to every one of these problems if I ever do get it done, because it's not a too terribly well-known book. And come on, who's buying Real Analysis books anyway? So I think I'm already in a very small minority of people for having purchased this book. A smaller one for going through every exercise and trying to solve all of them, and an even smaller one for uploading it to the internet. So maybe that leaves me the only person, but maybe not. It's called Weal Anawysis Wednesday, but this is probably going up on Sunday or Monday, depending on how editing goes. I currently have done the first 11 exercises of chapter 1. I think mostly good. I am a human, so if you're a PhD candidate or something and you want to roast me in the comments, go ahead and go for it. I'll just farm you for engagement. But I thought, now's probably a good time to get started. So I'm going to assume that if you're watching this, then you kind of know about set theory and basic quantifiers and how to read math, like what this guy means, and general kind of proof ideas, how proofs go. If you're not, then there's a video by struggling grad student, cool guy, doesn't know I exist, cool guy. The guy who I'm doing this video in the style of, with the one hand holding the camera and the other one with the pen and the going through. So he has a video on how to read math. It's a good video. He explains it all well. So and that was a good time to get started with this. So first, chapter 1, exercise 1, is a proof question. He gives us a proof a proof, in quotes, that 2 equals 1, and I'm supposed to find the mistake in it. So I went ahead and I transcribed it over here. X equals y, then x squared equals xy, if and only if x squared minus y squared is xy minus y squared, if and only if x plus y, x minus y is y, x minus y, if and only if x plus y is y, if and only if 2y equals y, if and only if 2 equals 1. And line 4 is where we get in an issue. This, if and only if this is bad, because if x equals y, then x minus y is 0. And the assertion that 0a equals 0b implies ab, or implies a equals b, is bad. And that's illegal math. And I've listed a counterexample. A is 1, b is 2, then 0a is equal to 0b, because they're both 0. But 1 is not 2. If you see a proof on the internet, it's like a cool math proof, contradiction, math, 1 equals 2. It's one of two things. It's either this trick, division by 0, or it asserts a squared equals b squared implies a equals b, which is also illegal math, because counterexample, a equals -1, b equals 1. A squared equals 1, b squared equals 1. So a equals b, or a squared rather, equals b squared, but a is not equal to b. So this was pretty easy to spot, just because I've seen a lot of those videos, and I know that basically they have one trick. Next one, number 2. We've got a bunch of statements here, and we're asked to find the truth value of them and give an example or like an explanation. So for every n in n, there's an m in n such that m is bigger than n. But basically this is saying there is no biggest natural number, which is true. So if I let n be a natural number, then take m equals n plus 1, then m is bigger than n, and m is a natural number. This one, for every m in the naturals, there's a natural that's smaller than it. This is not true. It looks incredibly similar, but they switched around the m and the n. And because of the way this keeps the order, we still have m greater than n. This is now false. So counterexample, m equals 1. There is no natural number smaller than 1. 0 is not a natural number. Fight me on that. It's not. C. There is a natural number such that for every natural, m is bigger than or equal to n. This is false, of course. I said true, take no, bad, we were bad. To be like, if you saw true and you were like, oh, that makes sense. And no, it's not. This is asserting the existence of a biggest natural number, which there isn't. Because again, if we take that number plus 1, we get a bigger one. There is a natural number such that for every natural number, m is greater than or equal to n. This is true. N equals 1 is the smallest natural number. So there exists a number such that every natural number is at least that number. That's true. E, there's a real number such that for every m, that's a real number, m is at least n. That's false. That's false for the same reason. One of these is false. I don't fucking know. But if we let n be a real number, we can take m to be n minus 1. That's still a real number. So n would be smaller, or m would be smaller than n, rather. For every integers x, y, where x is less than y, there's an integer. I wrote this in a funky way. The book says there exists z such that x is less than z less than y. This is the same thing. Where z would be an integer, of course. This can be seen to be false. We take 1 and 2. There's no integer between them. And then for g, this is the same question, but for reals. Z is real. And we can just take z to be the midpoint between those two reals. That'll be a real number in between them. All right, then for the next one here, we are playing more games with sets, which Jay Cummings in the book talks about like boxes. So we got boxes of stuff. Boxes can have boxes in them, etc. That's how he like makes an analogy for sets. So I'm supposed to describe each of these things in terms of boxes. This is a set minus. I'm going to be, whenever I deal with set minus, I'm going to be writing it like this. Just because I think it's clearer. I think you can't like confuse this with any like modulo thing from algebra. We take this might be construed as like B mod A, which I don't want to like offer as being misconstrued. So A minus B would be everything that's in box A that's not in box B. So we got a box, let's draw our box. This is box A. This is box B. A minus B, let's say A has 1, 2, 3, and 4, and B has 3 and 4. Everything that is in A that is not in B is 1 and 2. These are in A, and also they're not in B. So this would be A minus B. The power set of A would be, if you don't know, power set is the set of all subsets of a set. So this would be every possible collection of elements of a box A. That would take a lot of time to draw, so I'm not going to do it. And then C, cardinality A, just the amount of elements in box A. So I just count them. I labeled these with numbers, so they're going to be easy to count. So it'll be 4. There's 4 things in here. There's only 3 and 4 in here, so the cardinality of this is 2. There's 2 things. Then we have some more games with sets. Went ahead and transcribed this problem. A1 to AN are all boxes where n's natural. Describe each of these in terms of boxes. So the union of all of them would be everything that's in at least one box. It's kind of the definition of a union. So if I have A1, A2, A3, and I have 1, 2, 2, 3, 4. Let's do 1, 2, 3, 1, 2, 3, 4, and then 3, 4, 5. Then if I unioned all of these, union, let's make it like a script A or something. God, what a nightmare. This would be 1, 2, 3, 4, 5. It's everything that's in at least one box. And then B, the intersection of all these sets, everything that's in every box. So if something is in all 3 boxes, then it's in the intersection. The only thing in all 3 of these boxes is this guy, 3. So this would be 3, the set containing 3. 2 is in A1 and A2, but it's not in A3, so it's not in all of them. Similarly for 4. 1 is not in these 2. 5 is not in these 2. So only 3 is in all of these boxes. So only 3 is in the intersection of all the boxes. You got another problem about sets and stuff. Oh, you know what? Seems I didn't do that one. I only did this one. I only did A. What am I doing? Okay. So I guess I started on this one. A union B equals A, if and only if B is contained in A. I'm going to use this for contained in, because my topology professor rubbed off on me too much, and now I don't even make distinctions between subset and proper subset. So that's just where we're at right now. So we got A union B is A equal to A if and only if B is contained in A. So first, suppose the left side, then you want to prove the right side. So if A union B equals A, then X is in A union B implies X is in A. Because these two sets are equal. So if X is in one of them, then it's in the other one. Thus, if X is in B, then X is in A. Because if X is in B, then X is in the union of A and B. Since X in here implies X in here, then X in B implies X in A. Therefore, everything in B is in A, so B is contained in A. Now we want to go the other way. We suppose B is contained in A. Then if X is in B, X is in A. It's the definition of containment. We also have that X is in A implies X is in A, because the set is equal to itself. All sets are contained in themselves, rather. So if at least one of X is in B or X is in A, then X is in A. So the union is contained in A. Okay. We also have that A is contained in A, so A has to be contained in A union anything else. So since A is contained in A union B and A union B is contained in A, two-way containment implies the sets are equal. I'm actually going to come back to the rest of this once I'm done filming the rest of this. Then I'll do that live. All right. This might be where we start to see some mistakes and some work that I have scratched out. I think I'm going to leave that in. I don't want to make these pages perfect. I want to let you guys see me fumble around for a right answer. So we have 1.6. More stuff about functions and subsets and images and stuff. So if we suppose f from x to y, where x and y are sets, is a function, a is a subset of x, and b is a subset of y, I'm supposed to prove that the image of the inverse image of b is contained in b. Okay? So I let x be in that image. And then if we let c be the inverse image of b, then I can write c is in the image of, x is in the image of c. Then x is in this set. And so I let X be, and I keep like not being productive for a while. And I get to here. So I let Y, because I realized kind of pretty late that the variable would be in Y and not X, because the function goes from X to Y. So I let Y be in the image of that inverse image. Then there's some X in the inverse image of the set, such that f of X equals Y. So Y equals f of X for some X in the inverse image. Now here I make a claim that I felt like needed proof, so I underlined it and I proved it later. Since X is a function and X is in the inverse image of B, then f of X is in B. So f of X equals Y is in B. So I started assuming that Y was in the image of the inverse image, and then I concluded that Y was in the set. So that proves containment. So now I'm going to prove this underlined thing. X is in the inverse image of B. Since X is a function and X is in the inverse image of B, then f of X is in B. So I suppose, to the contrary, that f of X is not in B. Then X maps to some Y naught that's not in B. This is a Y. It's a Y naught. Oh God. Some Y naught that's not in B. And this is in Y. And it's not in B. Okay. This means that either f maps X to some Y1 in B and some Y naught not in B, which contradicts that X is a function? No, that f is a function. Sorry about that. F maps X to some Y1 in B and some Y naught not in B, contradicting that f is a function. Or X maps only to some Y naught not in B, contradicting that X is in the inverse image of B. So this assumption ends in contradiction, so it must be false, so its negation must be true. So f of X has got to be in B. Okay, now I'm supposed to give an example where the image of the inverse image of a set is not the set. So we only proved containment. We didn't go both ways. So if I let X be A, B, 1, 2, 3, and Y be B, B, 1, 2, 3 as well, and I defined F by, I just drew a picture because I thought it would be pretty clear. If I map everything in A to a single point in B, then the image of the inverse image of my set is not the whole set. Because the inverse image of my set would be A. Everything in here maps to something in this set, but the image of this set is not the whole of B. It's just one thing in B. F inverse of B, that's the inverse image of this set, would be this entire set, but the image of this set is not the entirety of B. There's some stuff the function doesn't hit. And this is fine because like it doesn't make any assumptions about being one-to-one or onto, just that it's a function. And this is a function. So that's fine. Now we have something kind of similar. A is contained in the inverse image of the image of A. So I let X be in A. then f of x would be in the image of a. That should be obvious, which is contained in y. Since f of x is in the image of a, then there's some y in the image of a, such that f of x equals y. Then x is in the inverse image of the set containing y. So x would be in the inverse image of the image of a. So a is contained in the inverse image of the image of a. X is in the inverse image of y, and y is in the image of a. So x is definitely in the inverse image of the image of a. And I'm to give an example where a does not equal the inverse image of the image. So I did a kind of similar trick. I made an x and a y. I made just this to be a and just this to be b. I mapped everything in x to one of 2 points in b, and a is not the entirety of x. So the image of a would be b, but the inverse image of b is this entire set, which is bigger than a, so they're not equal. Okay, and we're on to 1.7. This one I actually solved a different way. I did this one other time. I tried to solve a bunch of problems in this book. And I solved this a different way. I still have that piece of paper. So suppose f from x to y and g from y to x are both functions, and that g composed with f is the identity from x to x. So it just sends everything to itself. Show f is 1 to 1 and g is onto. I did this time by contradiction. I did it the other time by just verifying that the properties were true. But by contradiction, if I suppose f is not onto, suppose f that is not 1 to 1, then there are a distinct pair of elements in x. That's what this means. That means these are different elements in x, such that they map to the same output. Since g is a function, g of y naught must map to only one x naught in x. I don't make any stipulations about it not being equal to either of these. So if g maps y naught to x1, then g composed with f evaluated at x2 is not x2, and if it's the other way around, then it's still not the identity at a different point. So both of these things contradict that g composed with f is the identity on x. Now suppose that g is not onto, then there's something in x that g doesn't hit. There's some x in x such that x is not in the image of y under g. Then exactly this g of f of x is not x, which is pretty easy to get a contradiction of g composed with f is the identity. It took much less ink. It was pretty easy. Okay, now we have some De Morgan law stuff. A intersect B complement is A complement union B complement. I tried to do this by two-way containment at first. So I supposed it was in one. I actually, and so then that ended up not panning out. I wrote, let's do it a different way. And this is much easier. This only took 3 lines. So A intersect B complement would be everything in X, where I let X be the universe. I'll write that down. Oh, here it is. X is the universe. So it's everything in X that's not in the intersection. So it's everything in X that is, I just pulled this negation out front. Everything that's not in this intersection, which means it's everything that's not in A and B, which means if I use De Morgan's law here and I push this negative in, I have to flip this. So this is everything that's not in A or not in B, which is everything in A complement or B complement, which is A complement union B complement. And it's similar for the other way around. Everything that's not in A union B is everything that's not in A, is not everything that's in A or everything in B. Which I used De Morgan's law, push this in, got to flip this guy around. So X is not in A and X is not in B. So X is in A complement and B complement. So A complement intersect B complement. Prove that root 3 is irrational. The proof that you see that square roots of primes are irrational, they actually just prove that they are not rational, not that there is some real number that equals them and it's not rational. We're going to handle root 3 being a real number later, because I think there's an exercise like that somewhere down the line. I'm pretty sure I recall that. So first I'm just going to handle root 3 not being rational. If I suppose to the contrary, that it is rational, then there are some integers such that root 3 is the ratio of those integers, where n's not 0, and these two are coprime. That's what being rational means. I got interrupted by a friend there. All right, so where was I? That's all right. The definition of a rational number is that there's some integers such that their ratio is the number, and they can be coprime. So then, if I square both sides here, m squared over n squared is 3, so m squared equals 3n squared. Thus 3 divides m squared because n squared is an integer, and 3 times an integer is m squared. That's the definition of 3 dividing this number. So 3 divides m. This works because 3 is prime. So if 3 divides m times m, then 3 must divide m or m. So 3 must divide m. And that means there's some integer L such that 3L equals m. 3 divides m, so 3 times something has to be m. Then 3L squared. So I'm using this here. M squared equals 3n squared. So this is m squared is equal to 3n squared, which means 9l squared is equal to 3n squared, which implies that 3l squared is equal to n squared, which means 3 divides n squared and also 3 divides n, which contradicts GCD mn being 1, because 3 divides both of them. So the GCD would be at least 3. Thus the assertion that root 3 is in Q has to be wrong. Now, actually, the next question is, what goes wrong when we try to assert this same thing for the square root of 4? Square root of 4, as we know, is 2. So trying to prove that it's irrational is bonkers. I did a bunch of stuff with like LCMs and multiplying around before I realized that the thing that goes wrong is actually really early. This right here is illegal math. 4 divides m squared implies 4 divides m. That's illegal math. Just for an example, 4 divides 36. 4 does not divide 6. Pretty simple. This right here only works because 3 is prime. That's the statement of the lemma. 3 has to be prime for that to work. Now for C. C was pretty interesting. It took a lot of doing and a lot of crossing out. It states that I'm to show that root 3 plus root 5 and root 3 minus root 5 are either both irrational or both rational. And then I'm supposed to deduce that they're both irrational. So I tried a bunch of stuff here. Suppose that you know, I tried to prove in general that a rational times an irrational is irrational. That would, like, handle it. If A and B are real numbers, and A times B is rational, then either A and B are both rational or both irrational. This is handled by if A is rational and B is irrational, then their product is irrational. So that's what I proved. It's somewhere in here. I supposed somewhere. Yeah, here we go. Suppose not. Without loss of generality, say A is rational and B is irrational. Okay. Then I use this. This is what the assumption. Then AB is rational, means AB is some m over n, where m and n are integers. And since A is rational, A is some, what was that, a k? It's a k over L, where k and L are integers. So that means KLB, k over L times B is m over n. This is true if and only if B is equal to m times L over k times n. Since all of these things are integers, this whole thing is rational, which contradicts B not being rational. So they must either both be in Q or not in Q. Oh yeah, also forgot to mention that both of these A and B are not 0. That's kind of important. Okay. So root 3 plus root 5 and root 3 minus root 5 are not both in Q. This is what I'm supposed to prove. The rationals are closed under addition. They're a field. So root 3 plus root 5 plus root 3 minus root 5 would also have to be rational. But this is root 3 plus root 5 plus root 3 minus root 5, which is, we can cancel out these 5s here, these root 5s here, and just get 2 copies of root 3 plus root 3, which is 2 root 3. 2 root 3 is irrational by this very proof right here. So they are both not in Q. I guess I didn't really state clearly that this is supposed to be contradiction. So if both in Q, then yeah, then their sum would also be in Q. 1.1, we're almost to the end of what I've done. Prove the multiplicative identity in a field is unique. So basically, I let 2 things be the multiplicative identity and I showed they're equal. I'm pretty sure all of this is legal math and it does prove this thing, but it looks really short. So E1, which is one of the multiplicative identities, we can multiply that by anything, and it'll still be that thing, because this is an identity. So E1 is equal to E1 times E2, right? E2 is a multiplicative identity. So E2 times E1 should just be still E1. Okay. Now E1 is also a multiplicative identity. So E1 times E2 should also be E2, which means these 2 things are equal by transitivity, since they're equal all the way across. And now 1.11. Given an ordered field F the positive elements of F are a non-empty subset P of F, such that if two things are in the set, then their sum is in the set and their product is in the set. And if something is in the field that's not 0, then either A is in P or the opposite of A is in P, but not both. This is a XOR. I'm pretty sure that's a XOR. I'm not actually sure. I can look it up later. I'm supposed to find some subset of the reals that satisfies 1, but not 2. So it's closed under addition and multiplication, but you know what? This actually satisfies this vacuously. Oh, no, wait, it doesn't. Lol. Never mind. False alarm. If A is in the field and it's not 0, then either A is in P or not negative A is in P. If I just take 0, the singleton set 0 as a subset of the reals, this satisfies 1 but not 2, because 0 plus 0 is 0 and 0 times 0 is 0. But anything that's positive or negative is not in this singleton set. And it's supposed to find a P2 that's kind of like the opposite. That satisfies 2 but not 1. So I just took the positive reals minus 0. I guess I didn't need the minus 0 because positive is already without 0. Then if there's something in the field that's not 0, it's either less than 0 or greater than 0. AKA negative A is positive or A is positive. And then I wrote, but no, that's good lol, I guess. You know what? This isn't good. This satisfies 1. Doesn't it? Yeah, so I actually can fix that. If I get rid of, if I just change this to be a union. There we go. Then we still have, like, 3 is in here. And negative 3 is not in here. And this number 2 requires that the thing we pick not be 0. So like 0 and negative 0 are in here, but that doesn't matter because that doesn't fulfill this hypothesis. Whew, I was sweating. I thought I was going to be on that for some time, but no, this is good. And this doesn't satisfy 1 because we take oh shit, you know what? That's bonkers. Wait, this is harder than I thought it would be. I thought it would just be the complement of this, but it's not. Or like something similar. But no, I gotta do some thonking. So like just 0 and the positive reals, or just the non-negative reals rather, that doesn't work because that satisfies closure. Right? So that didn't work. So what if I just like remove a point? Yeah, what if I do this? What if I go R plus union 0 and then union negative 1 minus 1. So I let A be in the field that's not 0, I let it be -1, that's in the thing. If I let it be 1, then negative it is in the thing, but 1 isn't in there. And this doesn't satisfy 1, because if I let a and b be a half and a half, then 1/2 plus 1/2 is going to be 1. And similarly, any two numbers that are like multiplicative inverses of each other aren't going to satisfy this either. Now, isn't that something? Pretty sure that is actually a right answer. Okay, now I'm going to go back and do that one that I didn't finish. All right. So I ended up finishing 1.5. There it is. You can go ahead and take a look at those. So I already did this one. I came back to do B, C, and D. I actually ended up switching the order of C and B because I looked at it wrong in the book. So let's do B next. A intersect B is equal to A if and only if A is contained in B. So first I suppose A intersect B is equal to A. Then if X is in A, that means X is in B and X is in A. So I'm using like equality this way. I'm using A would be contained in A intersect B. Thus, if X is in A, then X is in B. So A is contained in B. Then, suppose that A is contained in B. Then, if X is in A, X is in B, and also X is in A, since A is equal to A. So X is in A implies X is in B and X is in A. So X is in B intersect A. So now we have A is contained in B intersect A. Now I suppose that X is in B intersect A. Then X is in A. So B intersect A is contained in A. So A is equal to A intersect B by two-way containment. Then C. A minus B is equal to A if and only if A intersect B is the empty set. So I suppose A minus B is equal to A. A minus B, that's the same thing as A intersect B complement. A intersect B complement equals to A. So if X is in A, then X is in A, and X is in B complement. So A is contained in B complement. So if X is in A, then X is not in B. So everything that is in A and B is nothing. Everything that is in A is not in B, so they don't share any elements. Okay, now I suppose that A intersect B is empty. Then if X is in B, X is not in A. And similarly, if X is in A, then X is not in B. By contrapositive, you just switch these around and negate both of them. So if X is in A, X is not in B. So everything that is in A and is not in B is just everything that's in A, because nothing that's in A is in B. Okay, now for D, A minus B is empty if and only if A is contained in B. Sorry, got a little burp there. So first, suppose that A minus B is empty, then A intersect B complement is empty. So it's not the case that there exists something in A such that X is not in B. If there were, then this would not be empty. Everything that's in A and is not in B is nothing. So it's not the case that there is something that's in A and not in B. This is true if and only if I use De Morgan's law, I push that in. For all X in A, it's not the case that X is not in B. This is true if and only if for every X in A, X is in B, which implies that A is contained in B. Now for the other way, I just suppose that A minus B is not empty. Then there's some X in A that's not in B. So A is not contained in B. That one's pretty easy. And then that would be up to 1.11. which is all I did for this Weal Analysis Wednesday. I'm going to try my hardest to get through the whole book. I'll let you know how that goes. Maybe there's another one, maybe there's not. If there's no next video, then that's just a shame. But hopefully I make more.